My name is Dr. Mike Murphy. I'm an assistant professor of computer science and information systems at Coastal Carolina University. In this lecture, I will continue the discussion of virtual memory by discussing paging performance and introducing demand paging, copy on write, memory mapped files, and shared libraries. Swapping pages to and from a backing store is a relatively slow operation compared to a direct access to RAM, due to the fact that most backing store hardware is several orders of magnitude slower than RAM. Whenever a page fault occurs, the memory access that triggers the page fault will require more time than a non-faulting memory access. As long as the number of pages swapped out to the backing store is relatively small compared to the total number of pages of memory in the system, the performance cost of page swaps is amortized over all memory accesses. As a result, the average memory access time is increased by only a small amount relative to a system that does not swap out pages. However, if the fraction of memory accesses resulting in page faults becomes too high, the system begins swapping, or thrashing, its memory on most or all memory accesses. This situation typically occurs when memory becomes oversubscribed due to a program bug, and the result is a system that is painfully slow to respond to user input. In some cases, on some systems, the OS may need to be rebooted to recover from a swapping situation. With any paging system, it is necessary to decide on a virtual memory fetch policy, which determines how data are loaded into memory pages for the first time, typically when a program is started. A lazy implementation of page fetching is to use demand paging, which loads a page from the backing store into RAM only when it is actually required. This approach improves the overall responsiveness of the system and increases the degree of multiprogramming at the expense of reducing the initial performance of newly started processes. The main alternative to demand paging is prefetching, which loads some pages into memory before they are actually needed. Prefetching may waste some memory by loading data that will not be used. However, it does improve the startup performance of many software applications. For this reason, prefetching is a fairly common feature of desktop operating systems. When memory is limited, or electrical power is severely limited, a pure demand paging approach to fetching may be appropriate. Pure demand paging does not prefetch any pages, including the text segments of newly started programs. When a new program starts, a page fault occurs at the first instruction, and the first page of the program code is loaded into memory. Pure demand paging has the greatest potential to increase the degree of multiprogramming, particularly in situations where physical RAM is extremely limited. In addition, the lack of prefetching can save CPU and memory operations, thus providing a small power savings when operating from battery. As such, pure demand paging could be useful on smaller embedded systems, especially monitoring devices and other systems without direct human interaction. While the fetching policy has a high impact on newly started programs, a copy on write approach improves performance whenever a process makes a copy of itself. On Unix-like systems, new processes are created when a running process clones itself with the forked system call. Cloning all memory at fork time could be a slow operation, since a process might be using a large number of pages. Copy on write addresses this performance issue by having the clone initially share the original process's memory pages. These shared pages are marked read-only, causing the MMU to fault if either process tries to write to them. The operating system handles this type of fault by copying the page and turning off the read-only bits on both the copy and the original page. This diagram illustrates the copy on write process. In the top half of the diagram, the original process forks a child process, which initially shares the original parent's pages. The child proceeds to modify page 3 in the bottom half of the diagram. When this modification is attempted, the MMU raises a fault that traps into the operating system. The operating system makes a copy of the corresponding memory frame, gives the copy to the child process, and removes the read-only setting on both the original and clone page. The child's page is then updated with the modified value from the memory write, and normal process execution resumes. In addition to increasing the degree of multiprogramming by enabling pages of memory to be swapped out to a backing store, the virtual memory subsystem can also be used to improve I/O performance for processes on the system. When programs request I/O from persistent storage devices, these requests generally take a significant amount of time to fulfill due to the relatively slow speed of the persistent storage device. Since many processes perform frequent reads and writes of small pieces of data, the performance overheads caused by waiting for device I/O to complete can become substantial. The virtual memory subsystem can be made to reduce this overhead by memory mapping files. Page-sized pieces of a file are loaded into memory where they can be read and written efficiently. These pages are periodically written back to the persistent storage device. As is the case with paging in general, there is no requirement that memory-mapped files be mapped into contiguous regions of physical memory. Logical addressing is used to present an ordered, contiguous, logical view of the file to the process. However, the file may be mapped out of order in non-contiguous memory frames. Although the file will be put back in order when it is stored to disk, the file still might be non-contiguous if the file system is fragmented. To reduce the total amount of memory required by a program, and to make software development easier, certain programming routines are implemented in shared libraries, which can be used by multiple programs on the system. When these libraries are used by a program, they must be made available to the program when it runs. In the simple case, which defeats the memory-saving potential of shared libraries, the compiler may statically link or copy the library into the program executable at compile time. A more efficient approach is for the loader to link the program to the shared library at runtime. On disk, precompiled shared libraries are stored in binary form as shared objects or .so files on Unix. These libraries are called dynamic link libraries or DLLs on Windows. Runtime dynamic linking of these shared libraries relies on read-only shared pages that can be used by multiple programs at the same time. Shared libraries are made available to processes by mapping them into the middle of the logical address spaces of each process, between the stack and the heap. These shared objects limit the maximum size to which the stack or heap can grow before running out of space. A situation in which shared library mapping becomes a problem is when virtual machines are implemented on 32-bit hosts. The hypervisor process on these hosts has a maximum logical address space of 4 GB. When the hypervisor tries to allocate a large contiguous block of memory to provide RAM to the guest system, the allocation could run into the shared libraries, resulting in a failure. I have seen this type of failure occur on a 32-bit host when trying to allocate a contiguous block of just over 1.2 GB on a Linux system with 4 GB of physical RAM. It is for this reason that a 64-bit operating system is desirable even for physical systems with only 2 to 4 GB of RAM.